The Foundations of Geometry by David Hilbert. Chapter 4, The Theory of Plane Areas. Section 21, Equality of Content and the Measure of Area. In Section 20, we have found that polygons having equal content have also equal measures of area. The converse of this is also true. In order to prove the converse, let us consider two triangles, ABC and AB'C', having a common right angle at A. The measure of area of these two triangles are expressed by the formula f of ABC equals 1/2 AB times AC, and f of A'C' equals 1/2 of AB' times AC'. We now assume that these measures of area are equal to each other, and consequently we have AB times AC equals AB' times AC', or AB is to AB' as AC' is to AC. From this proposition, it follows, according to theorem 23, that the two straight lines BC' and B'C are parallel, and hence, by theorem 27, the two triangles BC', B'C', are of equal content. By the addition of the triangle ABC', it follows that the two triangles ABC and AB'C' are of equal content. We have then shown that two right triangles having the same measure of area are always of equal content. Take now any arbitrary triangle having the base G and altitude H. Then, according to theorem 27, it has equal content with a right triangle having the two sides G and H. Since the original triangle had evidently the same measure of area as the right triangle, it follows that, in the above consideration, the restriction to right triangles was not necessary. Hence, two arbitrary triangles with equal measure of area are also of equal content. Moreover, let us suppose P to be any polygon having the measure of area G, and let P be decomposed into n triangles having respectively the measures of area G1, G2, G3, and so on through Gn. Then we have G is equal to G1 plus G2 plus G3 plus ... plus Gn. Construct now a triangle ABC having the base AB equals G and the altitude H equals 1. Take upon the base of this triangle the points A1, A2 through An-1, so that G1 is equal to A1, G1 is equal to the segment A1, A2, ... and Gn-1 is equal to the segment A(n-2), A(n-1), and Gn is equal to A(n-1b). Since the triangles composing the polygon P have respectively the same measures of area as the triangles A1C, A1, A2C, ... A(n-2), A(n-1c), A(n-1bc), it follows from what has already been demonstrated that they have also the same content as these triangles. Consequently, the polygon P and a triangle having the base G and the altitude H equals 1 are of equal content. From this it follows by the application of theorem 24 that two polygons having equal measures of area are always of equal content. We can now combine the propositions of this section with that demonstrated in the last, and thus obtain the following theorem. Theorem 30. Two polygons of equal content have always equal measures of area. Conversely, two polygons having equal measures of area are always of equal content. In particular, two rectangles are of equal content and have one side in common, then the remaining sides are, respectively, congruent. Hence we have the following proposition. Theorem 31. If we decompose a rectangle into several triangles by means of straight lines and then omit one of these triangles, we can no longer make up completely the rectangle from the triangles which remain. This theorem has been demonstrated by F. Schur and W. Killing, but by making use of the axiom of Archimedes. By O. Stolz, it has been regarded as an axiom. In the foregoing discussion, it has been shown that it is completely independent of the axiom of Archimedes. However, when we disregard the axiom of Archimedes, this theorem 31 is not sufficient of itself to enable us to demonstrate Euclid's theorem concerning the equality of altitudes of triangles having equal content and equal basis, theorem 28. In the demonstration of theorems 28, 29, and 30, we have employed essentially the algebra of segments, introduced in section 15, page 29. And as this depends substantially upon Pascal's theorem, theorem 21, we see that this theorem is really the cornerstone in the theory of areas. We may, by the aid of theorems 27 and 28, easily establish the converse of Pascal's theorem. Of two polygons P and Q, we call P the smaller or larger in content according as the measure of area f of P is less or greater than the measure of area f of Q. From what has already been said, it is clear that the notions equal content, smaller content, larger content are mutually exclusive. Moreover, we easily see that a polygon which lies wholly within another polygon must always be of smaller content than the exterior one. With this, we have established the important theorems in the theory of areas. The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice. This ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Wrenholt. Programming and illustrations by Jim Wrenholt. 2019. Portrait of David Hilbert by Reida Wrenholt. Thank you for listening.